Yeah, let's quickly start with our lesson so that we can be able to cover everything we are planning to do for the day. Uh, okay, Patu, I saw your questions on WhatsApp, so I'll attend to questions immediately after I finish with my class today. Uh, so, as I said in the group, today we're going to cover the topic about drawing the cubic graph. But let me just browse through what we have done under this chapter of calculus. So up to so far, we have covered a chapter of uh, uh, differentiation by first principle. Differentiation by first principle. And I believe all of you can be able to differentiate by using first principle because we have covered that in detail. And then the second topic we have done is what is called differentiation or to differentiate. That's one and the same thing. Differentiate by rule. I believe you can also do that. You can be able to differentiate by using rule as well. And then the third topic we have covered together is the topic of limits. You must all be able to approximate the given expression by using the limit. I also gave a quite detailed about limits. Remember, all these topics are under calculus, so you need to know everything about calculus in order to attend to this. So today we're going to cover a very broad topic of which I would like to also put a star on top there because this topic is very critical. It contains a lot of marks of which you must not lose even a single mark from that section because it's not difficult, but it's quite detailed. So it's for drawing cubic graphs. So that we are going to do today. So I will have to show you how you draw the cubic graphs. So now, I know you haven't done cubic graphs up to this function. So it's either we say cubic graphs or cubic function. It's one and the same thing. So it's cubic graphs or cubic function. So up to so far, we have covered straight line function, exponential function, logarithm function, parabola function, inverse function. So those functions we have done in detail. So today I'm going to introduce a new function which is called cubic function. So, but before I introduce that function, I would like to find out from you if there is any one of you who is introduced to that function from school up to so far, or it's going to be for the first time you hear about cubic functions.
For me, it will be for the first time hearing about cubic functions. Remember, I did my matric in 2015.
All right.
Me too.
Part two, is it going to be for the first time you see these cubic functions?
Yes.
All right. So it means I will have to explain this in detail. Little, she's not yet in. I believe she will be able to join later. Dakaro has given apology, so we'll have to give a recording. So now, let me explain this topic in detail since you haven't done it from secondary school. And as I've said, you can see from the 4 topics we have on the board, this topic I'm going to cover today, I put a star there because it's a very, very important topic as compared to the other ones. Even though the other 3 are important, but this one is the utmost important topic which you must know. All right, so let me introduce that topic to you just now. So drawing cubic graphs or cubic functions. So the very first thing which you need to know is the formula that represent the cubic function. That represent a cubic function. So cubic functions, they are given by this simple formula, which I'm going to write for you now. So it's f of x. So this is a function which you can replace by g of x, h of x, but the most popular one, they use f of x. F of x is equal to ax cubed plus bx squared plus cx plus d, where a, b, c, and d are all constants. So these are all constants. So constants, it means they can be replaced by any value. You can have certain value and then replace these constants A, B, C, and D. So, but the general formula for cubic function, it must have this term. So you can see if this term is not there, this function we have here is a known function. Can any one of you tell me, if we remove this first term here, which function will be that? Which function is going
It's a quadratic.
Is going to be a quadratic or a parabola, right?
Yes.
Yes, but now we have added another important term here, which is ax cubed. So this ax cubed, it makes this function to no longer be quadratic, to no longer be parabola, but it's now called a cubic function. Just by adding this first term here, we change the whole function to be what is called cubic function. So let me just give you an example of the cubic function, of how these functions, we can draw them. So I will just give an example by one function for cubic function. So this is another example of what is called the cubic function. So now you will see that if we omit this other part of the function, we're going to have a very known function that you have dealt with before. Again, if we remove this other part of the function, we're going to have a very known function which we have dealt with before. Can any one of you tell me what kind of function we're going to have if we remove the other part of this function here? What kind of function are we going to have?
If you remove which part?
This part here. And we
The parabola.
we're going to have a parabola graph. Do you see that?
Yes.
So in summary, cubic function is just an extension of parabola graph. Cubic graph is just an extension of parabola graph. So take note of that. So in other words, why am I relating the two? Because the properties which are in parabola function, there also appears on this cubic function. For example, let's talk about the turning points. We know parabola graph have turning points. So even the cubic function have turning points. So the difference is that for parabola graph, we have just one turning point. So for example, if we remove this part and we're left with this, we're going to have this turning point that we have up there. So that will be for the parabola. But now you will see that for the cubic graph, instead of having one turning point, how many turning points do we have? We have two turning points. So that's the first property, which relates the parabola and the cubic function. So for the parabola, how many turning points do we have? We have one turning point, right? And then for the cubic function, how many turning points do we have? We have two turning points. You don't go beyond that. You don't go beyond two turning points. Because some of you may assume that if we have another part like this, then still that is a cubic function. is not going to be cubic function if we have another turning point here or another turning point there. The maximum turning points for cubic function, how many are they? There are 2. Are we together? Are you with me?
Yes. Yes.
If you see any function which have more than 2 turning points, that is not a cubic function. Get me right on this one. If you see a function having more than 2 turning points, that is no longer a cubic function. It's something else, of which I will talk about later. So let me wrap that part which I added just now. So that's the first property I discussed with you about the turning point. Let me write it here in detail. So I believe you understood, but at later stage, I will have to explain that part again. So now let me go to the second part, which relates the cubic function and the parabola functions. These points we have here. So you can see we have that point there, we have that point there, and we have that point there. So if you remember very well, I gave these points name. Is there any one of you who remember what are the names of these points here? The points which are exactly on top of the x-axis. What do we call these points?
Intercept.
These are the points of intercepts or the roots, because some examiners, they like to confuse students. Instead of using the word x-intercepts, they might say roots. So you must know it's one and the same thing. So now, the other important things which you must take note of are these roots we have here. So for parabola graph, let me remove this part again. For parabola graph, is there any one of you who can tell me how many roots do we have for parabola?
2.
We have 2 roots, exactly. So is this root we have here and that root we have there. So with this function we have on the board, you can be able to tell me how many roots do you think we can have for cubic function?
3.
We have 3 for cubic function. Take note of that. So let me write it down. That is the second point, which relates the parabola and the cubic. So it's the x-intercepts or the roots. So now I will also elaborate further of how we calculate the roots for the cubic functions, how we calculate the turning points for the turning points. Is totally different with how you calculate the roots and the turning points for the parabola as for the cubic as compared to the parabola. Is totally different. So for now, I'm just giving you a summary of what relates the turning points and the x-intercepts. So now,
Sir,
yes.
can you write the spelling of roots?
Spelling of roots is R-O-O-T-S.
Oh,
Yeah.
thank you.
This is the root. So now, let me go further to discuss about what relates the parabola and the cubic function. So one more thing which relates these 2 functions is the x-intercept. Both the cubic and parabola graphs have just one y-intercept. They don't go beyond that. They only have one y-intercept. In other words, these graphs, they're gonna just cut once along this line on the y-axis. So those are all the properties, and we can't find the inverse of this function. There is no inverse for cubic function. So I hope you are with me up to this point. Is that so?
Yes, sir.
Are we together?
Yes.
All right, all right. So at this moment, I would like to explain to you of how do we calculate the turning points for the cubic function and the x-intercepts for the cubic function. So, but before I do that, I would like to find out from you, if you remember, how do we calculate the turning points for the parabola graph? Just remind me about that. How do we calculate the turning points for the parabola graph? Is there any one of you who remember this formula? X equal to negative b divided by 2a. Do you remember that formula?
Yes.
Yes. So this formula, we use it to calculate the x value on the turning point. So let's say this is a parabola graph. If you want to calculate the x value on this point here at the turning point, you don't have any choice except to use this. So x is equal to negative b divided by 2a. Don't forget this formula. So to calculate the x value, you must revisit your notes. It's there. I gave this in detail. To calculate the x value at the turning point, you use a formula of x equal to negative b divided by 2a. And then after obtaining the x value of this turning point, you then have to substitute this x value back to the main function. You calculate the x value back to the main function so that you obtain the y value. And then after obtaining the y value, you will then have the turning point. So the turning point is just this coordinate on top of the graph there. So that is how you calculate the turning point of the parabola graph. So now I would like to tell you how you calculate the turning point for the cubic function. So that I'm going to write here on the board. So it's 1a because we are discussing about the turning point here. How to calculate turning point of cubic graph. So let me tell you without any hesitation that the method we use for calculating the turning point of the parabola graph, it does not work here. We cannot use it to calculate the turning point there. We can't use it to calculate the turning point of the cubic graph. So let me do that by an example. How are we going to calculate the turning point? Let's say we're given the function, in this case, I'm just using a function g of x. It's the same. I could use f of x. It's the same as I'm using a g of x, which is equal to a is negative x cubed plus x squared plus x minus 1. I believe you can all agree with me that the function g of x, which I wrote on the board just now, is a cubic function. Do you all agree with me?
Yes.
Yeah, that is a cubic function. Why it's a cubic function? Because of this term, of the first term we have on the board there. Negative x cubed, it makes this function to be a cubic function. As simple as that. You don't have to explain more than that. You just go and observe the first term. Once you have a term of x cubed, then you can then conclude that the function we have is a cubic graph. So now I would like to tell you of how you calculate the turning point of the cubic graphs. You need to differentiate. You have to differentiate this function here. By now you know how to differentiate. So we're going to have g prime x. G prime x So g prime x is simply to say we are going to differentiate the function of g with respect to x. Are we together?
Yes.
What is the differentiation of this first term here? We have done that before. What do we get when we differentiate the first term here?
Won't it be negative 3 to the power of 2?
Is negative 3x to the power of 2. And then what do we get when we differentiate the second term?
It is 2x to the power of 1.
2x to the power of 1, which is the same as 2x, right?
Yeah.
And then what's the differentiation of x?
It will be 1.
Very true. What is the differentiation of negative 1?
It falls away.
Yeah, and I would like to find out from you why negative 1 falls away. What is the reason for omitting or discarding negative 1?
So you just cut, you jammed. What was the question?
What is the reason for cutting or for discarding the last term, negative 1 there?
Isn't it because it's a constant and a constant is always equal to 0?
Very true. Don't forget that statement. It's very, very important on differentiation. So at all times, even though you have a very big number, you must know when you differentiate a constant, you are going to get a 0. Are we together?
Yes.
All right. So now we have differentiated this function here. Remember, our goal is to calculate the what? The turning points, right? So we have differentiated this function here. The last time I explained to you what is g prime x. What is this g prime x? I gave you a name of that. What is this g prime x?
Some derivative or something.
Yeah, it's the derivative, but we have a special name for that, which you usually use from lower grades. Is the gradient, ne? That is the gradient. So we now have a gradient there. Patu? Patu, are you here?
Yes.
All right, I just wanted to find out. So this is the gradient we have here. G prime x is the gradient of which we obtained by differentiating this function, and then we obtained that. So I will want to explain this in detail from what we have on the graph there. So now the gradient at the time point is always 0. Because you can see, if we talk about the velocity, at this point, what is the velocity? It's like if I throw this marker up, so it's gonna reach certain point. At that point, when it changes direction, the velocity is 0. It will no longer be moving. It will be having a velocity of 0. So the gradient at this point, or the velocity at that point, at g of x is equal to 0. Even down here, g prime x is equal to 0. Let me emphasize again why g prime x is equal to 0 at this point. Because g prime x is velocity, and the velocity at the maximum point or at the turning point is equal to 0, because it's not having any velocity when it is changing direction on that point. It's like here it was going up, and now from that point it's now changing direction. So it's no longer moving, it's not having direction. It's not going upwards, it's not going downwards. Therefore, at that point, it's having velocity of 0. Therefore, g prime x at that point is equal to 0. Even down here, g prime x at that point is equal to 0. So therefore, on this function, you must let g prime x to be equal to 0 in order for us to calculate the x values at these points here. Remember, we have 2 turning points there. So you let this g prime x equal to 0. So it means you're going to have negative 3x squared plus 2x plus 1. And then that will be equal to 0. Do you all see where this 0 is coming from?
No, may you
Yeah.
please explain it again? I'm confused.
All right, let me explain again about this 0 that we have. So now let's go back again on this variable here. G prime x, I said that is our gradient, of which gradient is a velocity, right? Are we together?
Yes.
So this is our velocity or our gradient. So what I am saying that at the turning points, at these points here, the gradient is equal to 0. Why? Why am I saying gradient is equal to 0 at the turning points? Because it's like you are throwing this marker upwards to the upwards direction and it reaches certain maximum point. So, and then it changes direction and goes downward. So at that point, when it's changing direction, it's having a 0 velocity, like what we have here. So if you see on that graph we have on the board, so the this motion is going upwards, and when it reaches turning point, it then changes direction and goes downward. So on that point up there, it's having a velocity of 0 because it's a point. Turning point is a point where an object is not having any direction. It's not going upwards, it's not going downwards, because it's not moving at all. So it's having a velocity of 0. Hence, we have to equate this with 0 because g prime x is a velocity. So velocity at the turning points is equal to 0. Hence, where we have g prime x, we substitute 0. And once we substitute 0 here, we're going to have this expression we have down there. Is that okay?
Yes.
All right, wonderful. So from here, I believe you can be able to attend to that. Can any one of you tell me what can we do in order to find the values of x from that equation we have down there? What do we have to do from this part here in order to obtain the values of x from here? What can we do? We have to factorize, right?
Yes.
Yes. So we have to factorize in this case. So let's factorize and see what we obtain. So the negative is a problem. So let's deal with negative first by dividing with negative throughout. So we will obtain 3x squared minus 2x minus 1, and then that will be equal to 0. Then we factorize this. Remember how to factorize. So we're going to have 3x here. We have x there. We have 1 here. We have 1 there. So there we have negative. There we have positive. So it means we're going to have x which is equal to 1 over 3 or x which is equal to 1. So it's negative 1 over 3 and x equal to 1. So these are the x values at the turning points. So it's these values we have here, the x value at this point and the x value at that point. So after obtaining these x values, we must then substitute them back to the original function, this function of g of x. So when we substitute negative 1 over 3 into that main function there, can any one of you tell me what are we going to get? If we substitute this x equal to negative 1 over 3 back into this main function, what are we going to get?
Hmm. 1 over 3 divided by 1 over 3 minus 1/3. Hmm. I get negative 1,25.
Can we write that in fraction form?
It is negative 34/27.
All right, wonderful. Did we get the same thing, Patu?
I got 0.
All right. Let
Hmm.
me verify with my calculator. Okay, let me find out from you. When you substitute here, did you put brackets there on this term and that term? So you must have brackets, right?
Yes.
So we're going to have negative 1/3 to the power 3 plus negative 1/3 squared plus negative 1/3 minus 1. Yes, myself, I'm getting negative 32/27.
Yeah.
Is that so?
Yes. Yeah.
All right, Patu, make sure you put the brackets there when you do these calculations.
We are using which function?
We are using the original function. This one.
Oh,
Yeah. All right. So now let me find out what you get when you substitute x equal to 1 in order for us to obtain g at 1. What are we going to get?
0.
Get 0, right? Did you all get an answer of 0?
yes.
All right. Wonderful. So we have 0 there. So just by having that, you now have your turning points. So you have your turning point down here, which is negative 1/3 is to negative 32/27. And then up here, we have a turning point of 1:0. And that's all. That's how you're supposed to find the turning points of these functions. For sure, these turning points are not for this function exactly. So, but I'm just illustrating that this value is for that turning point we have down there, and that one is for the turning point we have up there. So, but I will tell you in detail of how do you know the turning point you obtained here is for at the bottom there, and the turning point you obtained down there is for up there. So that I will tell you in detail at a later stage. So for now, I wanted to cover only the part of finding the turning point. So I would like to find out from you where you did not understand when we find the turning points of this function. Where did
Sir,
yes.
I have a question about the factorizing. Ne? I
Yeah.
usually struggle with that one, yeah, the 2 brackets. I go that long route of, I don't know what's the name of it, but of negative b is equals to negative b square root of 2, yeah, times that long method of factorizing.
Yeah, the quadratic.
And then you do, yes, that one. Is it still fine, or do I have to go with the bracket one in this case, in the cases that will be coming up in the exams?
That is still fine. I think they cannot mark you wrong when you use that method because the question will not be specific that you must use the factorization or the quadratic. So I don't think it's not going to be wrong. But my advice would be try by all means to understand this method since it's going to save your time. So, but if maybe it's not possible to understand that this factorization, go for quadratic formula because it guarantees the solutions you obtain.
All right.
So it's not wrong to use quadratic formula.
Okay, then, thank you.
All right. So as I've said, that is the first part for calculating what? The turning points of the cubic function, right? So there's a second part which I still want to cover with you before we wrap up for the day. Is for calculating the x-intercepts of the cubic function. So that is another important thing, which if you manage to get that for the day, I can be very happy. If you are able to calculate the turning point and you are able to calculate the x-intercepts of the cubic function, I'll be very happy if you are able to do that. Can we go to the second part of calculating the x-intercepts of the cubic functions?
Yes.
All right, wonderful. So then we wrap up here. I'm not going to wrap that function since we are still going to use it. So I'll use the same example to explain this concept of calculating the x-intercepts. So I will name it 2a. So that is how to calculate x-intercepts. How can we calculate the x-intercepts? So of which I'm going to explain that by using exactly the same function of g of x equal to negative x cubed plus x squared plus x minus 1. So I want to use the same function to explain this concept. So now tell me, what is the value of y at these points at the x-intercepts or at the roots? What is the value of y?
0.
Y is equal to 0, very true. What is the variable that indicates y on this function given here? What is the variable that indicates y on this function given here? We know y is equal to 0 at the x-intercept. So this y equal to 0, we must substitute it somewhere here on this function. So I'd like to find out which variable indicates y on that cubic function.
G of x.
It's g of x, very true. So where we have g of x, we're going to replace by y equal to 0 or by 0. Why? Because we want to find the x-intercept, and at the x-intercept, y is equal to 0. Therefore, g of x, we must substitute 0 there, so that we have 0 equal to negative x cubed plus x squared plus x minus 1, of which you can write it in a better way, where we can say negative x cubed plus x squared plus x minus 1 equal to 0. You haven't violated any rule by doing so. You are allowed mathematically to rewrite this expression here as that. So it's a matter of saying 0 is equal to this, which is the same as saying this is equal to 0. You haven't violated any mathematics rule. Is that okay?
Yes.
Is that fine?
Yes.
All right. So now, whenever you see a negative there, you must be concerned. So let's deal with the negative on the first term. So you can divide through by negative so that we're left with a simple expression to deal with. So we're going to have x cubed